Hey friends, welcome back to the channel. Today we're taking on a question that falls into the equilibrium unit. Specifically, will a precipitate form when we mix two aqueous solutions together? We have both solutions, barium chloride, sodium sulfate, and the concentrations are given. Now on the surface, this question doesn't seem so bad, right? All we need to do is compare Q to K. We're going to calculate Q. KSP is given to us in the problem, and we know that if Q is bigger than K, a precipitate forms, whereas if Q is smaller than K, we don't get a precipitate. Not so bad, right? Well, here's the caveat and why most people get confused when they actually get into this question. You see, the concentrations on these bottles are not the concentrations we're going to use in our calculation of Q. The problem states that we take 100 mLs of this solution and mix it with 10 mLs of the other solution. Now, why does that make it harder? Because that means with a new volume of 110 mLs, we need to calculate new concentrations for both of these solutions. Once we do that, we can plug them into Q, then compare Q to K as we said, and get our correct answer. Let's take a look at the steps involved.
Barium sulfate is used in medical imaging. Its solubility product is 1.08 times 10 to the negative 10th at 25 degrees Celsius. So it's ideally suited for this purpose because of its low solubility when a barium milkshake is consumed by a patient. So this is the first data point that I'm really interested in, which is to say this number right here. That is my KSP. Okay, and we already know that's going to be relevant as we're going to be comparing Q to that number. The pathway of the sparingly soluble salt can be easily monitored by X-rays. Okay, will barium sulfate precipitate if 10.0 milliliters of a 0.0020 molar sodium sulfate solution is added to 100 milliliters of 3.2 times 10 to the negative 4th molar barium chloride solution? So those volumes, those concentrations are going to be very important to us. Now, before we get into actual math part of this, I want to make sure everybody understands the reaction we're dealing with. This is a double replacement reaction. So we have the barium chloride and the sodium sulfate, and then they're going to react, they're going to swap partners, and we're going to get sodium chloride, which will remain aqueous, it'll remain in solution. So it's essentially a spectator. And then barium sulfate is the potential precipitate that we're interested in. So you can see that I've highlighted that in yellow. So what I like to do is take that full double replacement reaction, that complete chemical equation, and then translate that into a net ionic equation, where as you can see, I've isolated the two ions we're concerned with. They are the components that are going to make up the solid, the precipitate. So we've got our Ba2+, we've got our sulfate, SO4 2-, and they will combine to make barium sulfate solid. So I think it's important that before we get into the math, you really have a strong conceptual framework here in terms of what's the reaction, what's reacting, what don't we care about, the sodium, the chloride, and why is it that we're going to be super concerned about the barium concentration and the sulfate concentration? Because when we go to make our Q expression, as you see here, Q is equal to concentration of barium and concentration of sulfate. Now, of course, the barium sulfate solid isn't included in the expression because it's a solid. So all we have is the two aqueous components. Now, of course, once we calculate that Q, our mission is to compare Q to K, and we highlighted the K in blue in the problem up above. So how are we going to calculate that Q? Well, the key thing here, which I talked about in the intro, is that when we combine these two solutions, again, if you read the problem, it says if 10 mLs of one solution is added to 100 mLs of the other solution. So when we combine them, the new volume is 110 mLs. And you can see over here, I've drawn a little diagram of the 100 mLs of sodium sulfate and the 10 mLs of barium chloride. Those are both going to get dumped into one beaker. So now our new volume is 110 mLs. So as it says here on the screen, step one is going to be calculating new concentrations. Let's zoom out a little bit. And you can see that I've calculated new concentrations for both the barium and the sulfate. But let's talk a little bit about how I did that. So first of all, you're going to notice that I start those calculations off with volumes. 0.1 liters for the barium and 0.01 liters for the sulfate. Where are those two numbers coming from? Well, all I did to get those two numbers is I took my 10 mLs up here and my 100 mLs over there, and I converted them to liters just by moving the decimal 3 places to the left. And I want them in liters because molarity is moles per liter. So that's how I got the two numbers that you're seeing over here, 0.1 and 0.01 liters. Those were just converted from the volumes given to me. Now, the first step is taking that volume and asking ourselves, okay, if we're taking that small volume and we know this is the concentration given to us for the two solutions, how many moles are we actually going to have of the individual components that we're interested in? Now, again, you might be saying, what's 3.2 times 10 to the negative fourth moles over 1 liter? Where did that come from? That is simply the concentration that was given to us right here. I'm just taking the capital M for molarity and I'm changing that to moles per liter. And of course, I did the same thing for sodium sulfate with the 0.0020 molarity. Okay, so I hope so far you followed where all these numbers are coming from. This is all just given information. Now, the next step is I want to get to the moles of barium and the moles of sulfate. Why do I care specifically about the moles of barium and the moles of sulfate? Well, because as you see, those are the two things that are going to be included in our Q calculation. So I need to know what's the concentration of barium and sulfate. Now it turns out here that there's 1 mole of barium in every 1 mole of barium chloride, and it works out nicely for our sulfate as well. There's 1 mole of sulfate for 1 mole of sodium sulfate. So that's a way to just get rid of the BaCl2 and the Na2SO4 from our calculation and be left with moles of the two things we really care about, okay? We don't care about the chlorine. We don't care about the sodium. Those are our spectators. So now you can see I went through those calculations. I put them into my calculator. So as an example of how I entered that, for the first one, I just entered 0.1 times 3.2 times 10 to the negative fourth. And everything else there is just a 1, so I don't really have to do anything with that. And then I got 3.2 times 10 to the negative fifth moles of barium. Now, why am I dividing it by this 0.11 liters? Well, that's just our new volume from up here. Now, again, I converted to liters, right? So I've simply moved the decimal 3 places to the left. Now, for the sulfate, I got this number when I did the calculation, and that's moles of the sulfate. And again, I have to divide that by that new volume, the combination of the two solutions. So I'm taking the 110 mLs and I'm simply moving the decimal 3 places to the left and getting 0.11 liters. So now when you put these numbers into your calculator, you should get these two answers. These are our new molarities, our new concentrations, right? This one is for the barium, and this one is for the sulfate. And this is what we're going to plug into our Q expression, right? We're going to be able to solve for Q now. Now, everything on this slide, this image, this drawing is color-coded. So if you see a number and you're not exactly sure where it came from, make sure to follow the color backwards. So for example, the 0.11 liters in the denominator is in black. And if you go back up and look at the black writing, you'll see that I got that from the combination of the solutions, which was 110 mLs. So in step 2 here in green, I'm now finally able to plug in my concentrations into that Q expression, solve for it, and I get 5.22 times 10 to the negative 8th. And now in pink, we can compare QSP to KSP. Now, I don't want there to be any confusion. You might say, well, why in green did you just write Q and then in pink you wrote QSP? It's really all the same. We're dealing with solubility here, so we call it QSP, which just stands for solubility product. But it's not. It's calculated the same way as Q, as K is calculated. The little subscripts that you often see next to things like Q and K are really just giving you some context, like what kind of problem are you solving? If you're solving a problem that's in the context of solubility, you're likely going to see the SP there. So we're comparing Q, which is 5.22 times 10 to the negative 8th, to our KSP, 1.08 times 10 to the negative 10th. Now remember, this number came from the problem. That was given to us way up here, okay? I did not calculate that number. So when I compare the two, it's obvious that Q is bigger than K. So what does this mean? Anytime Q is bigger than K in a solubility problem such as this tells us that the solution is supersaturated. In other words, it's dissolved all of the ionic components that it's able to, and there's going to be excess, and it's going to come out of solution. In other words, this reaction moves in the direction of the products and precipitate forms. So that's a step-by-step guide on how to do one of these problems. Now let's just talk about some general strategy tips, and I'd love to give you an example problem that you can try on your own. All right, guys, let's talk strategy. Anytime you have to answer one of these questions where it's proposed that you're going to mix two different aqueous solutions together and you need to know whether precipitate forms, we're going to go through some similar steps. Obviously, we want to get to a comparison of Q to K, and we're going to have to calculate that Q. So the first thing we need to do, as we demonstrated, is find the concentration of the ions which make up our solid precipitate product. Remember, these ion concentrations need to be calculated because we have a new volume that's the result of two solutions being mixed. We're going to want to find the moles of each of the two ions using the volume used and the starting molarity of their solutions. Next, divide the moles of each ion by the new total volume to get your new concentrations. Now we can plug that into our Q expression, get a value for Q, and compare it to KSP. Again, if Q is greater than K, the solution is supersaturated and a precipitate is formed. If Q is less than K, no precipitate. Okay, let's do a practice question. Please pause the video, read through it, try to come up with an answer on your own, then unpause for the answer. So once again, we see this is a problem where the result is Q being larger than K, so a precipitate will form. Let's look at the actual steps and math involved in getting this question right. Please pause the video if you want to review the steps in detail. Okay, everyone, I just want to thank you sincerely for watching. I really do hope this content made solving these kind of problems easier for you. And really, if you still have questions, you're still confused, I would love to know what it is that trips you up when you're solving these sort of precipitate problems. Leave a comment and I'll get back to you as quickly as I can. Thanks again, and I'll see you in the next video.